Hey. Okay, so we are discussing Vegas algorithm, and the hope is that we manage to implement Vegas algorithm today. I'm trying to construct a reasonable homework for you on Vegas. I didn't quite finish it because it doesn't work for me either. So it used to work in the past, but today it didn't work. But by the end of this class, I guess we're gonna understand how to make it work. Okay, so we are discussing Monte Carlo integration of high-dimensional integrals, and originally we just wanted to code a simple brute force Monte Carlo where we throw random points into the volume and just evaluate average of the function. And for this, we wrote this simple Monte Carlo routine here, which is very easy to understand. And it's written in the way that is going to be similar to Vegas type of sampling. Namely, we are going to evaluate the function, not just one function evaluation, but batch function evaluations. So in this case, the batch is 1,000 points. So we evaluate function on the 1,000 points at the time. And here is the crucial line. Here we have the function integrand. Integrand is the function that user is giving as an input. And we evaluate this function on points XR, which contain not only the dimension of the function, which is the let's say 3-dimensional, 4-dimensional function that we integrate, but has n points, where n is the size of the badge. And so we need to of course have the function such as this, my integrand, which is able to evaluate function on 2-dimensional array. So again, XR is a 2-dimensional array of n badge times n dim. So therefore, when we evaluate our function, which is let's say 1 over minus cos 1 divided by 1 minus cosine x cosine y cosine z, we need to evaluate it on all the batch points at the same time. So we're taking the slice here. So all the batch points are evaluated at once, and we are returning also the array, which is of the size of n batch, doesn't it? So the output has to be of the size of n batch, is a 1-dimensional array. So the output is 1-dimensional array, the input is a 2-dimensional array, isn't it? Okay, so because we are returning n batch function evaluations at once. Okay, so therefore all the future integration, all the future functions that are going to be used in Vegas need to have this functionality, so that the input is a 2-dimensional array, the output is 1-dimensional array. Okay, and this my integrand is a perfect example of a function which can be speed up by numba, for example. Okay, so here you can add the this JIT in front of the function, and it will hopefully be much faster. I mean, this case is not essential because this step here uses NumPy evaluations anyway, and it's vectorized. So in this case, I guess NumPy will probably not improve much. But whenever you have slightly more complicated functions, function that needs to go over all the n batch points, then it's definitely a good idea to use NumPy to speed it up. Okay, so basically, I think that the rest of this function, or the rest of this algorithm, already explained before. I guess yeah. Well, let me very quickly repeat. So here we evaluate the function on all these points. Then we sum all the function values with the weight, no, actually, we just sum all the function values. Yes, there is no weights right now. We just do sum of all of I fi. Yes, just fi. So actually, this is wrong. So f of I. That's what we do. Then here we sum all the values of the function fi square like this. And in order to get the average of the function, we need to divide here by the number of function evaluations, isn't that? So then it's the real average of the function. And then this part here is the average square. So sum SQ sum, as you see here, sum SQ sum contains the value of the function square. Okay, and therefore, if we divide it by a number of function evaluations, we get the value of the function square, but then we take square root of that. Okay, so W0 is the square root of the average of the function. Now, why do we do that? Because we want to evaluate standard deviation in such a way that we don't hit overflow. Sometimes overflow can occur because these sums can be very, very large sometimes when you have a pole in the function. So therefore, we use the following trick. So this quantity f square minus f average square can be written as, well, as a usual math can be, you can write you can write the square in terms of the product of two terms, isn't that? If you square this thing, you get exactly the left-hand side, isn't it? So therefore, the first part, W0 here, is square root of the f square, isn't that? Square root of the s square. So this is W0. And then we need to subtract from W0 the average value, which is this thing here in the brackets. Okay, but we also need to add to W0 the average value. Okay, this is this second part, and then we divide by the function number of function evaluations and take a square root. Okay, so this cum error now is exactly the standard deviation of this function divided by n, and this is the error bar that we are expecting. Okay, and then we just multiply the final results with the unit to the power of dimensions, because if the integration is not between 0 and 1, but it's between 0 and pi, then the integral is actually, the volume is, of course, pi to the power of number of dimensions. In this case, for example, pi to the power of 3. So we need to multiply both the average and the integral by this volume, or the dimension of the volume, isn't it? The volume size, actually. Yeah. So this is the volume size of the hypercube. Okay. So this is the simple Monte Carlo, and we already explained how the function that we integrate needs to look like. So now let me evaluate this. Here we are gonna. Our unit is pi, because we said that we're integrating from 0 to pi. The dimension is 3, because we have 3-dimensional integral. So cosine kx, cosine ky, cosine kz. Then we're going to take a number of evaluations, 1, 2, 3, 4, 5. So this is less than 1 million. It's only 200,000. We know that exact value is 1.3932, which we can integrate analytically. And then we here instantiate these class cumulants, which we defined here. So this class cumulants is something that we're going to use in Vegas as well. Basically, just contains these averages over the current sampling. And then we are going to run this simple Monte Carlo function, and simple Monte Carlo function needs as the first argument this function integrand, and our function integrand is this my integrand 2. So we are giving my integrand 2 as the function to integrate, isn't that? That's like a pointer to a function. And then number of dimensions, we need to give number of dimensions here, number of dimensions, which is 3 in this case. Then the unit is pi, maximum number of function evaluations, and finally the cumulant that we need to give. And well, then we just evaluate the results after this sampling are written in this cum function, and cum average, as you remember, is the average is the average of the function times the volume, which is the value of the integral, and cum error is the standard deviation, is the error of our integration, isn't it? And of course, the exact value we know. So by knowing the exact value, we can calculate how wrong, well, how far from the exact value is our integral, how many sigmas apart. And we see that in this case, it's 0.4 sigma apart, but sometimes it's several sigmas apart. As we know, yes, 1.4, for example. As we know, the statistically, of course, there is a normal distribution, so it means that it's possible that the integral would be sigma or 2 sigma apart, although it gets less and less probable when we go into the details of the normal distribution. So this simple Monte Carlo works, but we want to make it much more precise. And the way to do it, as we said, is one way is Vega's algorithm. And what do we need in this case? Well, the first part that we are going to discuss is are the grid functions. So let me try to remind you what the grid functions are. So in this discussion here, we said that we are going to use this G1, G2, G3, and so on. These are the grid functions. So basically this function G1 of X, G2 of X, G3 of Z, and so on. So these functions will be contained in the class grid, and will be, there's going to be n one-dimensional functions, isn't it? N one-dimensional functions. Okay. So this is the grid. It contains these functions, Gn of X, and all these functions need to go from 0 to 1, isn't that? That's the idea. They need to go from, when X goes from 0 to 1, the grid functions not need to go from 0 to 1, but of course they are not exactly G of X is X. They are when we start iterating Vegas, they become non-trivial functions. Yeah, the constraint is that G of 0 is always 0 and G of 1 is always 1. But in between, the function can have arbitrary grid. Now, at the first iteration, we are going to just set G of X to be equal to X. So basically, we're going to just do this. Now you might ask yourself, why would we do that? Well, because we want to start writing Vega's algorithm, and for that we want to have proper grids set up so that we can write linear interpolation, a proper linear interpolation that is going to be used in Vegas. Okay, so so the first step. Grid is trivial, but we still need that grid in order to start building the code. So what's needed for this grid? Well, the input is going to be number of dimensions, which is the dimension of the integral that we are doing, so, or the dimension of the volume or which we are integrating, and then number of bins is these functions, these are one-dimensional functions which are defined on certain grid, which is uniform in the sense that it's a linear mesh, but has n bin points. Is that n bin points? So this n bins is going to be typically of the order of 100, maybe a little bit more than 100, but the typical value is between 100 and 200 bin points. And dimension in this case is just 3, but of course in general it can be much bigger. So the first thing here is we initialize the array of these grid points. We have to remember that the dimension is such that we first have dimension of the integral n dim, and then we have n bin points. The trick is that it's not n bin points only, but if we want to conveniently interpolate later on, we're going to use n bin plus 1. Why? Because we need the first point g0 of 0, and we need g1 of 1. So, and we're going to have actually not just n bin points, but n bin plus 1 points, actually, n bin plus 1. So now we discussed the points are going to be distributed in particular way that is convenient for fast linear interpolation. Namely, the first grid point x0 is going to be at point 1 over n, where n is n bin points. The next point is going to be at 2 over n, and the n minus 1 point is going to be at 1. And now, for convenience of linear interpolation, we're going to use many times x of minus 1. Okay, because when we are going to evaluate the entire array, it will happen that we are going to need value of this grid at minus 1. And that's nice because it turns out that the last value, well, in Python, x of minus 1 means takes the last value. Now, this G contains n bins plus 1 size of the array. So therefore, the last point, minus 1, is actually at n bins, which is at n. And so all we need to make sure is that the very last point here in this array at n bins will never be changed. It will always be 0. And if it's 0, then means that this is just for convenience, so that when we evaluate function, grid point at 0 is always going to be 0. Okay, so it's a little trick so that the equations look nicer. Okay, now what are we going to do at first step? At first step, we're going to just set g of x is x, which means that the grid points are well, x0 needs to become 1 minus n, x1 has to become 2 or n, and so on and so forth. And this expression is exactly that. This float n bins here is exactly 1 over n, and then a range from 1 to n bins plus 1 gives exactly an array of 1 over n, 2 over n, and all the way to n minus n divided by n. So the last point here is n divided by n, which is 1. So it means it sets x of n minus 1. But notice that it doesn't touch the last point, which is set to 0. So the very last point is always set to 0. Okay, so in other words, this little code just sets up the grid in such a way that g of x is exactly x, and x points are 1 over n, 2 over n, and so on. Okay, with the last point being set to 0. Okay, so let me evaluate this grid. And now that we have the grid, we can start writing the Vegas algorithm. Okay, so this first step, I mean, I'm gonna show you Vegas algorithm in 3 steps. Okay, 3 steps. Why do I do that? Because somehow if we code everything in one single step, there are too many things, and somehow it's hard to understand what's going on. So therefore, the step 1 is going to have just a basic setup. All the loops are going to be there, but it will not have a proper grid. Grid is going to be trivial, basically g of x is x, and it will not bin yet the function. It will not project the function to its to the axis. So we are not going to self-consistently change the grid yet. So in step 1, so basically step 1 is exactly equivalent to trivial Monte Carlo. in step 2, we are gonna I think in step 2 we are gonna start to evaluate those projections of the function to all the dimension, to all the axes, and then in step 3 we're gonna use this. We're gonna construct the new grids, and we are gonna then self-consist the self-consist the grids. Okay, so that's the plan, but we're going to go through it slowly. Okay, so what do we do in step 1 then? Integrand again is the function for which the integral is being evaluated. So it's function fx. This unit is the same as before, which is pi in our case, but in general, I will ask you for the homework to change this this unit to be basically an arbitrary interval from A to B. That's that, an arbitrary hypercube. So this thing will need to be changed for the homework. Then maximal is maximum number of function evaluations that we are asking the user to do. Yeah, so this is a little, this is a new thing in Vegas, n start and n increase. Now, n start means how many function evaluations we are gonna perform at the first step, because Vegas algorithm is iterative algorithm. So the first step will just sample the first approximation for grids. Okay, n start will just sample the first approximation for the grids, and then in the next iteration we're going to improve the grids, and then we're going to improve the grids again and again self-consistently, and every time we're going to slightly increase the number of function evaluations. And this n increase means how much we're going to increase, how many more function evaluations we're going to do at every successive step. So once more, at the very first step of Vegas algorithm, we're going to use n start points to throw into the volume. And this n start shouldn't be too small, because if it's very small, then we are not going to know, the grids are going to be awful. We're not going to know how the function looks like. So n start needs to be a few thousand points, or maybe even 10,000 points. Okay, we need to throw in to get some feeling of how these functions, how the function look like, how to create the grid. And then once we have some reasonable approximation for the grid, in next iteration, we're going to increase a little bit by n increase. We're going to increase a little bit those number of points and improve the grids, and so on and so forth, several times. So every successive step will have a little bit more function evaluations, but the entire number of function evaluations is going to be bound by maximal, which hopefully is, well, which is going to be probably around 1 million. Okay, and then the two classes are needed, grid and cum, and we discussed what this grid is. Grid is this class grid here, and cum is this cumulant, which contains all the average square, and projections, and so on. Okay, so now at the very beginning, we are going to here get a number of dimension and number of bins from the information that is contained in grids. So grids is the input here is grid, and grid already contains information about the dimension and a number of bins. So we don't need to use, we don't ask the user to provide this again, because it's already contained in the grid. So we just use it from there. Then we're gonna set up the size of the volume. So size of the volume is unit to the power of n dim. This is just the entire size of the hypercube that we're using. And then n batch here is again 1,000. So we're going to do 1,000 function evaluations at once. Yeah, at the beginning we set number of function evaluations to 0, and this is going to, of course, this is going to be changed in the course of calculation. And we are printing here some information about what was the input to the Vegas algorithm. Then this is an interesting array, bins. So this array bins is an integer array. Look at here, is D type is integer of size n batch and dim, which will tell you in which grid point the random number falls. Okay, so let me try to explain that. So when we linearly interpolate a function g, so what do we have here? Yeah, we are going to need to interpolate g of x. Okay, we're going to need to interpolate g of x. So x is a random number. Okay, x is between 0 and 1. It's a random number, and we will need to evaluate g of x. And so, how do we evaluate g of x? Well, we use linear interpolation, which is written here. Okay, but in order to do that, we need to know what is I. Okay, for linear interpolation, I, and this I, of course, is the grid point into which x falls, isn't it? So so what's the condition? The condition is that that x times n, just a second, x times so sorry, 1 divided by n, I minus 1 divided by n is less than x is less than I over n. Yeah, so that's how we need to find I, isn't it? So from this equation, we can evaluate what is the proper bin. Okay, so the proper bin is I here, is the variable I. Okay, so we're going to save those bins, so basically which point, in which grid point random number x is thrown. Okay, then currently in the first iteration, all n samples is n start, which means that currently we just do n start number of function evaluations, isn't that? So all function evaluations right now is just n start, because we are just doing the first step in which we are kind of getting the feeling for the function, or basically we're just building the grids, the first step in which we're building the grids. Okay, so here we need to evaluate all n samples values of the function, but in steps of n batch. So every time we're going to subtract here n batch, because we're going to, the entire number of function evaluations is going to be all samples, but every step is going to contain either n batch or a little bit less than n batch function evaluations, because in the last step we might need to do slightly less function evaluations in order to not overdo number of function evaluations. So this n, if n batch is commensurate with number of function evaluations that we need to do, then n is always going to be n batch. Okay, but otherwise the last step is going to contain a little bit less function evaluations than all previous steps. Okay, so this n then contains the real number of function evaluations that we need to do in this step, in this pass. Yeah, so why do we do this in batches? Why don't we do this? Why don't we do all n samples at the same time? Because we need to save, for example, lots of information. For example, where the bins are and where the points x are, and it's inconvenient to have a huge arrays. So let's say that the user asks for 1 million evaluations. We would need to have 1 million times n dim points saved if we didn't do it in batches, okay? But having batch of 1,000 points, it's not a big deal. So an array of 1,000 times, I don't know, dimension 50, 1,000 times 50 is still not a big array. But if somebody asks you to store million times 50 points, that's a huge thing that will take a lot of memory and will also slow down the code. So therefore, it's convenient to do this in batches so that we don't need to use too large arrays. Okay, so this VGH is going to be weight for each random point in the batch. So what is weight? Well, in naive Monte Carlo, weight is just 1 over n, but in our Vegas algorithm, weight is going to be more than 1 over n, but it's going to contain also those derivatives, basically Jacobian. So weight is this thing here, dg1 over dx, dg1 over dx times dg2 over dx to dg3 over dx. So this Jacobian times 1 over n. I mean, I guess here I didn't write 1 over n as I should have. Maybe there's a better formula somewhere. Yeah, I guess here, yeah. So the weight is going to be this 1 over n times the Jacobian, okay? dg1 over dx, dg2 over dy, dg3 over dz times 1 over n. So this is what we're going to be called weight. And then function is, we need to multiply this with function f in order to get the average f. Now here we need to be a bit careful because the weight is going to be dg1 over dx, dg2 over dx, dg3 over dx divided by n. But here we need actually 1 over n, not 1 over n squared. So here we square this thing, and we need this guy times 1 over n rather than 1 over n squared. And we will see that this little thing, one needs to be a bit careful that n here is not, doesn't come as a square, come as 1 over n. Okay, so weight here again is going to be just this Jacobian. Then XR here are the random points. So we generate here with this call random, we generate two-dimensional array of random points between 0 and 1. Okay, so how many? Well, n batch roughly, so the order of 1,000. I guess n batch is 1,000. We said, I think, n batch is 1,000. So it's going to be so it's going to be 1,000 times n dim, which is 3 in this case. So it's 3,000 points. 1,000 times 3 points, random points, and now we need to evaluate in this this loop here, this double loop. I wrote here that this part takes quite a lot of time, and it would be nice to rewrite with Numba. So I will ask you as a homework to try to insert Numba statements wherever possible. And in order to speed up this loop, which obviously is, well, we have two for loops. This is very bad if it's written in Python, and they're pretty large loops. I mean, 1,000 times 3, so 3,000. This is definitely convenient to rewrite in Numba. But in order to do that, you will need to have a new function which will be Numba jitterized. So basically it's going to have jit Numba, okay? Because the entire Vegas algorithm is definitely not going to be, we're not going to be able to make it jit-like. But this little pieces we probably can. And therefore, my feeling is, I didn't try that yet, but I will, that this piece, this particular piece that I highlighted here, would be convenient to have it as a separate function, for which we're going to be able to speed it up with Numba. Okay, but let me explain what this function does. Okay, so, or what this part of the function does. So basically, it evaluates. So let me return back. So it evaluates G. Yeah, it does this linear interpolation. g of x, okay? It does linear interpolation for all g's, and then evaluates all these weights. Okay, this is what it does. And let us see if it's reasonable, if it makes sense. So we clearly need to go over all points in the badge, which is 1,000 in this case, or all 1,000 points, and over all dimensions. Okay, now the weight here, we're going to start with the weight being just 1 over n. Okay, so and later on we're going to multiply weight with this derivative dg over dx over each dimension, So we're going to go through all dimensions from dim in range of n dim, and we're going to multiply here with dg1 over dx, dg2 over dy, dg3 over dz, and so on. Okay, so once more, we start with weight being 1 over n, and then we multiply dg over dx for every dimension. Okay, times n bins. Now, how does this n bins come from? Let me show you once more. So here, what we are going to do here, as I said, is that weight is we're going to start first to write it as 1 over ni. This is the statement outside the do loop, and then we're going to multiply it with dg1 over dx, but dx is basically 1 over n. Okay, and now we need to have discretized version of dg1 over dx, which is going to be basically delta g between 2 points. Delta g1, then it's going to be delta g2 divided by 1 over n, and delta g3 divided by 1 over n, and so on and so forth. Okay, so that's what we're doing. So once more, I hope that you see this thing, my writing. Do you see it? Are you following? Are you lost? Not yet. So basically what I'm trying to explain, that the weight is going to be written as 1 over n first, and then all these derivatives are going to be this function is function which is piecewise linear. So this derivative is exact. This derivative of the function is exact when you write as delta g as 1 over n, because the function, the grid points are these functions are assumed to be exactly linear, so they are not continuous functions. We make them non-continuous in the sense, well, they are continuous, but they are not continuous differentiable. So the idea is that they are exactly piecewise linear function. Therefore, these derivatives are not approximations; they're actually exact. Okay, for this particular function that we are doing. So that's important because we don't want to have systematic error. Because the number of grid points might not be so big, might be only 100. So therefore, if we approximate these things with approximate derivatives, that wouldn't be good. But here in this case, our grid points are not assumed to be continuously differentiable functions, but they are just continuous. Okay, so yeah, so this weight, it starts with 1 over n, and then it's going to be multiplied with these derivatives. Now let me see how these derivatives work. Now we need to go over all dimensions here, dimension 1, dimension 2, dimension 3, and we want to evaluate the function f at point g of x, isn't it? So we need f of g1, we need g1 of x, g2 of y, and so on and so forth. And here we basically transform points x, y, z into g1 of x, g2 of y, and g3 of z, and so on. And in order to do that, we need to evaluate g at those grid points. And I'm again repeating here how our mesh is constructed. So we decided at the beginning that our mesh is going to be constructed in such a way that t of 0 or x of 0 is going to be 1 over n, t of 1 is going to be 2 over n, t of 2 is going to be 3 over n, and t of n minus 1 is going to be 1, and then t of minus 1 is going to be 0. Okay. This is in the grid points, isn't it, in G. So, and we know the G of 0 is 0 and G of 1 is 1. So the G of minus 1 is always 0 and G of n minus 1 is 1. So to interpolate G at general point X, we do the following. We first calculate where is the grid point, the correct grid point, which is simply integer x times n. X is the random number, n is the number of bins. Okay, so x times number of bins gives us the grid point I, into which grid point this function is, this random number falls. And then once we know I, we can linearly interpolate function with this prescription. So we need to take some combination of gi and gi minus 1 times proper linear interpolation. Okay, I'm not going to go through this once more, but the point is we need to first calculate the proper grid point, and then we linear interpolate function between gi and gi minus 1. And we're sticking here the value x. Okay, so how is this done in practice? Oops, it's now moving all over the place. So how is this done in practice? So the first step here is to evaluate just to calculate just x times n. So xr are all our random points. Okay, this is a two-dimensional array of random points, and we take each random point here at the time, one random point at a time. Random point I here, I is from the batch, and dim is from the ndim. So we take one random point and we multiply with the number of bins. This is again like doing x times n. Then we take the integer value of this. So this is a typecasting. So we take the integer part of this thing, of this pos, okay, integer part, which we called I pos. And this I pos is actually the grid point, the I that we need, okay? And then we need to evaluate this gi at point I and gi minus 1. This is what's needed for both derivative and for the linear interpolation, isn't it? Both derivative and linear interpolation needs this difference, g of I minus gi minus 1, and this is what this thing does, grid of g. So we take the g from this particular dimension that we're interested in, so g of this dimension, and then we take of I pos minus 1. So again, gi minus 1. Okay, this is this quantity. Then we can write down the linear interpolation. So linear interpolation is going to be this difference which we just evaluated, gi minus 1 times this pos minus I pos, which is here x times n minus I, isn't it? So once more, pos was evaluated above as x times n. You see this is x times n here. So this pos is exactly the same as this x times n. Then I pos here is exactly the same as I. So we're putting this pos minus I pos as being x of n minus I. Then we multiply this thing with g of I gi minus 1. So this part here is exactly this, corresponds to this, diff pos minus I pos. Then we add to this, we need to add gi minus 1. So we are doing here gi minus 1, isn't it? And this is basically gx. Now there is one little trick here. We also multiply at the end of the day with unit. Okay, and this part is very important. We multiply with unit. So when you're gonna integrate not between 0 and unit, or 0 and 1, or 0 and unit, but from general A to B, you're gonna need to change this line. Okay, So how we're going to need to change this? So let me show you what you're going to need to do. This is something that they're going to ask you for homework. So if XR, if we are integrating from general point A to B, you're going to need to do the following. So we first evaluate the function gx. So this is still our function gx. Okay, but then you need to say that XR of I and dim is not going to be gx times unit. So naively, you would say just we are doing just this gx times unit, isn't it? We just stretch the interval from 0 to 1 into the interval from 0 to pi. Okay, we are just stretching it. Okay, but in a generic case, when we integrate from A to B, we're going to need to do this: gx times b minus a plus a. Okay, so do you understand why? This is for general integration from A to B, doesn't it? Because gx is the grid point that goes from 0 to 1. Okay, so this value will start at A and it will end at B. So we are stretching our grid from 0 to 1 into A to B. Okay, so this is how we need to generalize this step when we do it for a general limits from A to B. But for now, I'm going to comment this out because we don't want to complicate it yet. So at the moment, we're just stretching the interval from 0 to 1 to 0 to pi. And then in this step here, we are just storing the position, the grid points that we just evaluate. The problem is the following. In later steps, we are going to need to store the projections of the function to all the axes, okay? Because that's what Vegas needs, isn't it? We need to evaluate the projections of this function on all the axes, and we need to store them into the proper grid point. In this step, we are not going to do it yet, so therefore it looks like we are kind of storing something that we don't need, but it will become clear in step 2 or step 3 that this is essential. We need this. We need to remember this bin points in order to store the projections. Okay, so we are just remembering them. That's all. We are not going to use it currently. And then the weight, as I said, the weight is the accumulated Jacobian. So it's diff times n bins. So why is diff times n bins? Well, diff, as you remember here, diff was defined here, is basically gi minus gi minus 1, and the dx. We need to evaluate dg over dx, isn't that? And so dg is the difference between gi and gi minus 1, and dx is just 1 over n, isn't that? Dx is just 1 over n. So therefore, this is equivalent to multiplying with n, because it should be divided by 1 over n, which is multiplying by n. Okay, so so therefore this weight now. So this is just Jacobian from that dimension, okay? And we are multiplying, we are doing this times equal, which means that we are multiplying here over all dimensions. So for first dimension, second dimension, third dimension, and we start with 1 over n, okay? So weight now contains Jacobian and 1 over n. And then once we are done with all the dimensions, we are storing the weight into VGH of I, okay? So I goes over all the bin points, over all the batch points, or all the random numbers in the batch, and we are remembering this this weight, or this Jacobian of this function. Okay, so finally we managed to interpolate the function g of x for all relevant points in the batch. And now that we have this, now xr here is not just x, but it's actually g of x. So now we can just evaluate the function f on all these new xr points. So let me explain what exactly we're doing. So this step here, integrand is equal to x of r, is exactly equivalent to doing this. We are evaluating this function here. See this function, f of g1 of x, g2 of y, g3 of z. Why? Because in the previous step, we transform from x, y, z into g1 of x, g2 of y, g3 of z. Now xr contains these g's here, okay? And once we have these g's, we can just evaluate the function on this mesh, f of g1, f of g2, f of g3, okay? So in this step here, fx is equal to integrand of xr, we are evaluating function on all these grid points, okay? Because xr contains g1, g2, g3, g4, and so on. Okay, and well, next step is trivial. So we add here how many function evaluations we have done up to now, and then yeah. So this is within this batch. Yeah. So within this batch. So now within this batch we can calculate the average value of the function. No, sorry, the average of the function, yes, so which is f of I times v of I. So we multiply the values of the function times its weight. And now this weight, as I explained before, contains two things. The weight, once more, contains 1 over n and contains all these Jacobians, okay? So weight is this times this. As I explained before, weight contains this thing, okay? And the function, the function was just evaluated. So basically the average of f of v is just multiplication of the weight times the value of the function that we just evaluated. These two things, isn't it? So this is just the value of the function that we've just done. And then cum sum will contain, so this is in this cumulant, we're going to save the sum over all those over all these, the entire batch, or basically the sum over the entire batch of this functional values, is that with proper weights. Okay, so this sum here sums over the entire batch, because this v fun is of the dimension of the batch, which is 1,000 values, isn't it? So we are evaluating this function on 1,000 values at a time, and therefore we are here summing those 1,000 values into this cum sum. And then in the next step, we are trying to construct f square. Okay, basically we're just squaring. So v fun times equal v fun, which means that we're squaring this function. Okay, and then we are summing the squares of the function. Okay, so now let me explain here in this notes what are we doing. So we are first summing over the entire batch of this f, and we are also summing over the entire batch of f square. The only trick here is that this, you see, everything else is squared except 1 over n. 1 over n is not squared. Okay, so therefore this is equivalent to saying that we are gonna do 1 over n square. No, sorry, we're gonna remove this one. We're gonna put 1 over n square in here, 1 over ni, and then we're going to multiply at the end of the day with ni. You see, we didn't do anything yet. We just added here 1 over ni. We are always allowed to do that, which will then appear as 1 over ni square, and then we multiply at the end with ni for convenience. So that's what we're going to do. Okay, so once more, this weight contains 1 over ni. the weight already contains 1 over ni. So this is what is weight times F. And so now we just need to multiply the entire square with ni. Now where we're going to do that? Yeah, so we were doing this. Cum SQ sum is sum over square. So we are summing squares of the function. And then we're gonna, in this step, you see, we take this value of SQ sum and then we multiply with n. So why do we multiply with n again? Is because there was one n too much, okay? One n too much. Why? Because because here n appears inside the square, and then we need to multiply with ni at the end to get f square, the quantity that we're looking for. Okay, so now this, but now we need to calculate. This quantity, f square minus f average square divided by ni minus 1, and we're going to use the same trick that we used before, namely that this is fw square average square root minus fw I times the same quantity with plus. So the same quantity. Oops, paste. Bit of a mess, sorry. So this with plus divided by ni minus 1. Okay, so this is not so readable, unfortunately. But the point is that you can write this thing. You can write this thing as the product of two terms, doesn't it? One with minus and one with plus, and that's what we're going to do. So yeah, we take here square root of f square, and therefore we take later square root of f square minus the average and square root of f square plus the average. One is with plus and one is with minus, and this is the part that we need for sigma square, isn't it? And then yeah, we still need to divide this. Yeah, so now this quantity w now is 1 over sigma square. Why? Because we take n minus 1 divided by the quantity that we just evaluated, w1. Okay, so you see that this is exactly 1 over sigma square. So in other words, this quantity that we are evaluating here, w, is, so this is 1 over w, 1 over w. Because yeah, w itself, we said, is going to be, w is n minus 1 divided by this quantity. Okay, so w is n minus 1 divided by v1, which is this f square minus f average square. So now, in other words, w now is 1 over sigma I square, and then cum weight sum is the sum of all 1 over sigma I square. So let me try to remind you what cum weight sum is. Some cum weight sum is this quantity, okay? 1 over sigma I squares. One is gonna become 1 over sigma square best. Then cum au sum is the value of the average value of the function, cum sum, times this quantity, 1 over sigma square. So this reminds you of course, this quantity here, fw of I divided by sigma square. You see this function, this value, fw I divided by sigma square. This is called cum au sum. And then, of course, cum average is the ratio of the two, cum au sum, cum weight sum. Why? Because, well, this is, you see, we are doing this quantity divided by the 1 over sigma square is I best. So I best is then I best is the cum average. Okay, and then the error bar, cum error bar, is square root of 1 over cum weight sum, which is clearly 1 over sigma. No, actually sigma best, isn't it? It's sigma best, because 1 over sigma squared is this quantity, which we evaluate, and sigma best, of course, we can then is 1 over square root of this cum weight sum. Okay, and basically this is it. Then all we need to do is we need to multiply both the value of the integral and the sigma with the volume. Okay, this unit to the power of n dim. Actually, here unit to the power of n dim is something that we prepare here as unit dim, unit to the power of n dim. I guess we could use unit dim, but then we forgot to use it. Yeah, so basically the value and the error needs to be multiplied at the end with the volume. You need to be careful here that the average of the function has the proper has the same dimension as the volume, and the sigma itself has this proper dimension of the volume. It's to multiply with the volume, not sigma square. So if you try to multiply sigma square with the volume, you're going to get something that has nothing to do with error. It has to be sigma that has to be multiplied, the standard deviation itself that is proportional to volume. Okay, so this is the first step. Again, it looks like a very complicated part, but because it's the core of the algorithm. But the first step is basically just doing simple Monte Carlo evaluation by provided that we have the grid points g of x. Okay, so now what we're going to do is we're going to test this. Unit in this case is pi. We go from 0 to pi. We have 3 dimensions. We're going to take 200,000 function evaluations. We know the exact value. We're going to instantiate the cumulants just like before. Yeah, in a number of bin points. So we're going to take 128 points for this function. So we're going to bin all these functions on 128 grid points. And at the beginning, we're going to use 10,000 points. So right now, this step is going to contain only 10,000 points and not more than that. 10,000 points are going to be thrown into this volume from 0 to pi, 0 to pi, 0 to pi. And it will give us a first approximation for how the function look like, or how the new grids are supposed to look like. And then at every next iteration, we're going to add 5,000 more function evaluations. So in the first iteration is going to be 10,000, next iteration is going to be 15,000, and then next iteration is going to be 20,000, and so on and so forth. So every iteration we put in a little bit more function evaluations. Now this here we just instantiate the grids that we're going to need in Vega's algorithm. Of course, this grid, as we discussed, is completely trivial now. It's just g of x is x. Then this random seed starts a random number generator at the same, it's 0.0 in such a way that when we evaluate this several times, we are always going to get exactly the same result. That's convenient when you debug your code. So if you want to always have exactly the same result, not the same result within statistical error, but exactly the same result, we need to set your random number generator to predefined value of the starting point. So your random number generator always goes through exactly the same sequence of random numbers. So again, this is convenient for debugging. It's not a good idea for final evaluations of your Monte Carlo. Okay, so we are going to, and then we call our Vega step 1 with the function my integrand 2 that we defined before, which is this function that we're trying to integrate. Yeah, and we give all this things that we defined above: number of function evaluations, how many function evaluations we're going to do in the step, and this will evaluate the first approximation for the function, which of course has pretty large error bar. Well, not so much, but it should have. I mean, this is accidentally pretty good. In general, can be pretty off, but at this point, we just got some rough overview of the function. And now in the next step, Vegas 2, we're going to add the projection of the function to all the axes. So we're going to call this step Vegas 2, which is going to do which is going to evaluate this function f1 of x, f2 of y, and so on, from which we're going to calculate the new grid points g1 of x, g2 of y, and so on. Okay, so let me walk you through this Vega step 2. So everything up to here is exactly the same as before. This is also exactly the same, The only place where we change now is this line. So fx bin. So this fx bin will contain projections of the function to all the dimensions. Okay, and this is an array of the size number of dimensions times number of bin points, isn't it? So this two-dimensional array will contain projection of the function on all the dimensions for this batch of points. Now, where else did we change? So this part here is exactly the same. This is the same. This is the same. This is the same. So this hasn't been changed at all. Interpolation has been changed and will not be changed anymore. This is already done. This is correctly done. So the only new part is right here. So here we are actually storing the projections of the function to all dimensions. So we already calculated the projection of the function before. We just didn't store it. Why? Well, because this V fun here is the value of the function times its weight. Okay, that's what we need. That's our yeah. Okay, actually no. Later on we square this thing, and that's the quantity that we need for our weight. Okay, so let me explain this a little bit more precisely. So here I can now remove this notes from before. So this thing is what we need for constructing new grid points. Okay, so we just need to store. This value of this quantity into the array. That's all. So we need to know at which grid point this thing is falling, and we need to store it. Okay, that's all. So how do we do that? So as we said, this we fun here after we square it. So this line here squares the function, okay? Because as we said originally, we calculated the value of the function, we calculated this quantity, and then we square it. Now notice that when we square this thing, we have this issue with ni that I emphasized before, but for the for this new constructing new grids, this 1 over n is just a prefactor, just a number that it's irrelevant. We can just forget about it because we're going to need to normalize the function anyway. So once we normalize, this 1 over n issue is gone, and we don't care about it. So we just take this f square function, this f square. We take this v fun, which is the f square, isn't it? That has this extra 1 over n, but again, we don't care about 1 over n. And we take this function for this particular point in the badge, and we then remember it. We add it to the proper bin, okay? Because you see this bins here is the quantity that we saved before. So in this line here, this line, we calculated in which bin this grid point x falls. Okay, so each random number here, xj, yj, zj, we had to figure out in which bin does it fall. Okay, now that we know in which bin all of those fell, now we have to store this projection of the function on this proper bin. Okay, so we are saving here into this proper bin the projection of the function, or the value of this f square, this function, and we're going to use it later on to improve the grids. Okay, so all that we've done here is just use the previous quantities to save the projection of the function to all the dimensions. So again, v fun is something that we calculated before, which is the square of the function. And this bins is something that we already calculated before when we were linearly interpolating the grid points. We already had this quantity, and now that we have both, we can save the projection of this function. Projection of the function to all the dimensions. Okay, so I think that this is all in this step. There is absolutely nothing else that we've done here, changed here, except that we return in this step. We are returning this function projection to all the x's. Okay, so now that we have this projection of the function on all the x's, we can look at it and we can examine it. We can see roughly how the integrand looks like. Okay, so let me evaluate this, and then we're gonna evaluate this step once more, exactly the same as before. But now the difference is, so the only difference in this step is that we are saving, when we do the Vega step 2, we get as an output this projection of the function to all the dimensions, fx bin. Okay, and now that we have this fx bin, we can look at it. Okay, we can look at it and we can see how does it look. Okay, and here I'm plotting it. So fx bin of 0 is the dimension 0, dimension 1, and dimension 2. Isn't that fx bin of 0 is projection to dimension 0, fx bin of 1 is projection to dimension 1, fx bin of 2 is projection to dimension 2. And as we know, all those projections should be the same, because the function is symmetric with respect to x, y, and z. It's cosine kx times cosine kx z. So there's symmetry. So all those three curves are supposed to be identical, but of course they contain a lot of noise, and their normalization is very strange, in the sense that normalization is the order of 10 to the minus 7. But we understand why this normalization is so strange. It's 10 to the minus 7 because we were dividing 1 over n, and then we squared this thing. So basically, normalization is like 1 over n squared. So it's a very small value. We would need to multiply with n and then with proper volume and all the stuff to get good normalization. But we don't care about normalization. All we care about here in this step is the shape of the function, because we're going to normalize it anyway. Yeah, so the function does have roughly correct shape in the sense that the peaks we know are at the edges. So at the beginning and at the end, around 0 and around pi is where the peaks are. So let me remind you why this is so, because we are evaluating this function 1 over cosine kx, 1 over cosine ky, and so on. This function here we are evaluating, and as we said, it has peaks at it has peaks at 0 and it has peaks at pi. So we are basically evaluating this triangle here from 0 to pi, 0 to pi, 0 to pi. Okay, so that's what they're doing, and therefore, of course, if you project this to all the dimensions, we're going to see that there has to be a peak at the beginning and has to be a peak at the end. Okay, of course, this peak at the beginning comes from this projection, and then this peak, of course, appears here. Okay, so therefore, in other words, we expect the peak at 0 and at pi. So at both points, we expect a peak, and indeed, we got a peak. Okay, so this code seems to work properly. Now, the problem is that in the next step, we don't want to use this awful function that has here lots of bumps and dips. We want to kind of smoothen it out and want to make it slightly nicer. Okay, so how do we do that? Well, we discussed this last time. How to make it better? There are two tricks. One is just very simple. So we are going to average over 3 points. Okay, so we're going to take f of I minus 1, f of I, and f of I plus 1 divided by 3. So average over 3 points to smoothen out the peaks and dips, and then we're going to transform it with this function. Okay, so these are the two steps that we're going to do. Now this is implemented here. First, this smoothing function is exactly what we wrote over there. So it's x minus 1 divided by log x to the power of 1.5. Okay, so if x is bigger than 0, but if x is less or equal, well, it shouldn't be less than 0, it can be 0. If value of function is 0, then this returns 0. Of course, if we were naively evaluating x of 0, then we would get nuns, doesn't it? But of course, if we properly calculate the limit, then we know that x of 0 should be 0. But unfortunately, this function here is singular at x is 0, so we're not allowed to evaluate it. And now you see the trouble with this thing is that there is definitely a few bins that do not contain anything. Okay, because statistically we don't have so many points. And therefore, almost for sure, some points are going to be, some bins are not going to have even a single point in there. Therefore, if we didn't do this if sentence, if we didn't say if x is bigger than 0, we would definitely have nuns in our mesh. Okay, but we don't want that. So therefore, we need to have this if sentence. If x is equal to 0, then return 0. Now, the trouble with this is that once we have an if sentence, then this function is not anymore vectorized. Okay, so as long as you have an if sentence, vectorization of the function goes away. So we cannot evaluate this function on an array anymore. However, as you remember, in our introductory to NumPy, there is a function provided in NumPy which is called vectorize. So if we apply this vectorization on this function smvfun, we can get another function which is actually vectorized, and it can be applied to entire array. Okay, so therefore, VSMNsum is such a function which is vectorized on the entire array. And now, finally, this part here smoothens the function. So what does it do is, I guess I will probably need to go into details next time, that basically does that. But how does it do it? Well, it does it in the following way. Now, here I try to sketch. Okay, so this is original array. And then if you want to write the following, that fi is going to be fi minus 1 plus fi plus fi plus 1 divided by 3. If you want to do that, you can do this by shifting the arrays, isn't it? So you can take the original array like this, then you shift the same array for 1 unit to the left, you shift the same array for 1 unit to the right, and you sum them up. So plus, plus, plus. So we do this, plus this, and then you divide by 1/3 all the points in here, and then the edge point we need to multiply with 1/2. Okay, so that's how you do it with vector algebra. So instead of doing this, instead of iterating through the points, which of course in C or in Fortran you would iterate from points, in Python it's much better to use this vector type prescription, where you shift the array, shift left, shift right, and sum them up. Okay, and that's what we're going to do in Python. But this is going to be done, of course, next time, because today we're running out of time. So if there's any question, please ask question, or stay after the class to